right. Well, let's maybe do a little bit of review from what we were covering earlier. Let's do ammonia and water first. With ammonia and water, can you write down the products of this? This is going to be a Bronsted acid-base reaction. Tell me what you get. Somebody have it? And then the driving force also. NO3 and hydrogen gas. Try it. NO3. Good. NO3 minus or just NO3? NO3 minus and hydrogen. The reason I'm asking is this. With NO3, do you see, does that look funny to you or it looks okay? When I see NO3, it looks very funny to me. It looks very funny. This is like saying this. NO3 looks funny to me because it would be like, you know, when you burn paper like this, you can form soot, which is carbon. You can form carbon monoxide, which is CO. You can form carbon dioxide, which is CO2. You can form carbon trioxide, which is CO3, and carbon tetroxide, which is CO4, and carbon pentoxide, which is CO5. Does that sound funny to you? So when I see NO3, it sounds very funny to me. Can somebody explain why? Sounds funny. You can't explain why? Okay, how about can somebody explain why carbon trioxide sounds funny to me? Why or why not? Well, even this, we talked about carbon trioxide at length well before we talked about octet rule. Well before then. So you don't have to bring up octet at all for carbon trioxide. This was, I know it was a long time ago, but we want to review frequently from the beginning, since we're getting closer to the final exam. We want to start to take a look at that earlier stuff and see if you can remember it. And if you can remember it from memory, that's what you want. Then you know you're in a good spot. If you can't remember it at all, then you want to go back through. Sooner is better for the final exam, because people, and this happened to me as well, overwhelmed for the final. I was feeling a total feeling of being overwhelmed, like being hit by a tidal wave of information. And there's no way, there's absolutely no way you can drink. And some people say it's like drinking out of a fire hose. You know, you can't drink out of a fire hose. It's just too much, too fast. Yeah, but rather than drinking out of the fire hose, if you just distribute all that water over, you know, the course of the entire semester, then it's easy. So initially, when I started doing it, it was like drinking. Then I started doing this review stuff. So, you know, something like carbon trioxide, we covered that weeks and weeks and weeks ago. I would have already read through it a bunch of times, but does anybody remember it? Nobody remembers carbon trioxide? And that was like 30 minutes of your life wasted right there. Maybe. You know. Yeah, okay, that's exactly right.
Why? In carbon?
Yeah. Carbon trioxide would be +6, as Sheena's mentioned. But carbon doesn't normally run up to +6. Carbon runs from -4 to +4. Why is that? Because it's the valence shell. We didn't talk about the valence shell and the octet and the core back then. But the reason why is to get carbon in the +6, you have to remove core electrons. Core electrons are very hard. It's not to say you can't. It is possible, you know, if you have an extremely powerful oxidizer or something else, to maybe knock a core electron off. These are the types of connections. These types of connections only occur to people who have been thinking about it. You know, you think about it and then you can make the connection between, okay, we did this +4 to -4, you know, could you connect it to valence and core without somebody telling you, you know, and then you know you got it down, you know. And so this one, no, this one's a no-go, because what's nitrogen? Here, +6. What does nitrogen range from? -3 to +5. Yeah, that's a valence shell right there. You know, -3 to +5. And so there's no way nitrogen trioxide, if somebody, you know, automatically you would go, no, absolutely not. You should, you know, but it takes time. Now nitrate's okay, because nitrate is, what's nitrogen in nitrate? +5. So nitrogen here is +5, so it works out. So nitrate's okay, but then we have a huge problem. If it's nitrate and hydrogen, it doesn't work electrically. You know, we get extra electrons appearing because there's no positive. Somebody's got to lose if nitrate gains. So we have to come up with something else, maybe H+. But the other thing is this, you know, for peroxide acid base, and for all acid-base reactions, the oxidation state should not change. You know, the oxidation state does not change. The only time the oxidation state changes is in redox reactions. And so metathesis is an acid-base, we don't experience any change. There's a huge change in oxidation state, because ammonia is what we call electron-rich or electron-poor. Electron-rich, yeah, because -3. Nitrogen. -3 is going to something very electron poor, +5. It's losing a total of 8 electrons. Each nitrogen is losing 8 electrons. You got to have a powerful oxidizer to do that, to form nitrate. And so we want to think, Bronsted acid base, you fall back, we just did the chapter on acid base. And primarily we were looking at Bronsted. We did one Lewis, with carbon dioxide. But what was the Bronsted acid base reaction? What happened in Bronsted acid base? Yeah, we need to transfer hydrogen. So we have two choices. Ammonia loses a hydrogen or water loses a hydrogen. Which one is going to lose? Well, the stronger acid. What's a better acid, ammonia or water? Water is a better acid. So can somebody come up with the products for this particular reaction and then the driving force? Not do redox, but yeah, there's no driving. What are the products? Right. This is going to be an aside. First off, was there any change in the oxidation state here? So nitrogen's -3, hydrogen is +1. Hydrogen is oxygen. Good. Nitrogen +5, and that makes hydrogen what? -1. That's one possibility. The other possibility is this. Which one's more electronegative, nitrogen or hydrogen? Nitrogen's more electronegative, so nitrogen is more likely to take the negative charge in this case. And so here, if nitrogen takes a negative charge, or takes the electrons, it would be -3 and +1. So nitrogen didn't change, it went from -3 to -3. Hydrogen's +1 to +1, so it's okay. Over here in hydroxide, what is it? Well, oxygen's more electronegative, so that's going to get -2, and then hydrogen is +1. That usually works except for peroxides. The only exception to that is peroxide, which is H2O2. Here, because there aren't enough hydrogens here, oxygen is going to have to sacrifice. Oxygen cannot be -2 because hydrogen cannot be +2. And so we have to go with an oxygen at -1, and therefore hydrogen is +1 here. We don't have enough hydrogens to do it, so peroxide's the exception. Normally this is the way I do oxidation states. I do it by who's more electronegative, who's stronger at taking electrons. But there's no driving force because this is the base, and for sure we're going from weaker, which is ammonia, to stronger, which is hydroxide. And the same thing with the acids. Ammonium's a much stronger acid than water, which is a weaker acid. This is what we call qualitative. But if we want to do things more quantitative, then we got to understand that partial reaction can occur. But to be more quantitative, because when we say, okay, there's no driving force, well, is it black and white? No, it's not black and white. There could be some balls that can roll uphill. If you got this mix of balls, one way of thinking about it is how steep. Because if I have this mix of molecules, then we know about collision theory. In collision theory, we have a distribution of energies. And within that distribution, there are going to be some high energy molecules. Even at room temperature, there are going to be high energy molecules, right? And some of those high energy molecules might be able to go uphill or roll uphill. And so most of the molecules can. Most of the molecules are down here. There's not enough energy, but there are a few that can get high enough in energy to actually react. We saw this with water. You know, water at room temperature, most of the molecules aren't reactive. In fact, if I had 1 billion water molecules, about practically all of them don't have enough energy to react. Do you know about how many, though, might be able to roll uphill out of 1 billion?
Which one?
About 1? Yeah, close to 1. 4. About 4 out of 1 billion go uphill. And it's the same thing here. So to be more quantitative, you know, we know that in collision theory, you know, the bulk of these aren't because there's no driving force, but maybe some can defy this and actually react. So sometimes we care about it, sometimes we don't. You know, and the times we care about it, you know, if we want to be more quantitative, then we do equilibrium. Calculations versus standard stoichiometry. And so how much, you know, where does the balance lie? You know, it depends, you know, how unstable are the products, how stable, you know. Sometimes, you know, the no driving, it depends on how much of a hill it has to climb. Sometimes the hill is so steep, there's absolutely pretty much no reaction. Sometimes the hill is not that steep, and so there can be plenty of reaction. If the hill is not that steep here, and some of these balls can roll uphill, you know, go from lower energy to higher energy, then for sure we need to do equilibrium versus stoichiometry type calculation. We can see how steep this hill is depending on the K. You know, what was the K called again? I know it's been Thanksgiving, nobody wants to do any work, including me, so I did nothing over Thanksgiving, but do you recall what K represents? The equilibrium constant, and it's the ratio of what to what? The equilibrium constant is a ratio of you might not have written it down because it didn't really require it, but let's take a generic reaction. AA plus BB goes to GG plus HH. Then it's going to be the ratio of the concentration of G raised to little g, H raised to little h, depending on how many products we have, over A raised to little a, B raised to little b. These are all concentrations here. This is the equilibrium. So essentially it's this, it's products over reactants. And so we talked about the number. The number, if it's a big number, you have lots of product. If it's a small number, you have lots of reactant. And so the magnitude of the number tells us. And so this gives us a better idea, you know, rather than just saying no reaction, if we did an equilibrium type calculation, we could see, you know, maybe there's a little bit of reaction, we can figure it out. And so that's exactly, this is going to be a side. You know, I'm not going to have you do the equilibrium calculation here, but we're going to do one for this.
Do we need time for the exam?
This is not going to be for the exam. This is just for, you know, hopefully, I skipped pretty much the entire chapter on equilibrium with the calculation. So this is just an example calculation from all the stuff I skipped. So this, you've seen it before, but I don't really expect, you know. Like, I think one of the things that helped me is repetition for remembering things. So if you hear it once here and then forget about it, and then in Chem 1B, then you hear it, then you might go, oh yeah, I remember something like that. Versus if you hear it fresh for the first time in Chem 1B, you might go, wow, that's really
And so equilibrium, we use this. This is to indicate that there could be a little bit of back and forth here. This is gonna go to ammonium plus hydroxide. And then K, this is given or we determine it experimentally. The equilibrium constant here. You find in table or determine experimentally. We could do this also by theoretical calculations. Or use theory to calculate. Well, anyway, K for this is going to be the ammonium concentration raised to the first power times the hydroxide ion concentration raised to the first power divided by the ammonia concentration raised to the first. All the coefficients are 1. So 1 ammonia, 1 water, 1 ammonium, 1 hydroxide. Now water, interestingly enough, the water, pure liquids and pure solids are left out because the concentration doesn't change. And so water is omitted from this. Well, it's not. It's incorporated into this, but water is a pure liquid. And so if you had a gallon of water, it's pure. If you had a half gallon of water, is it still pure or is it not pure? It's still pure. And so water is a pure liquid. Its concentration does not change significantly. It's pretty much a constant. If you add a whole bunch of other junk in there, yeah, its concentration can change, but this tiny bit of ammonia is not really going to change its concentration. The concentration of water is about 55 mole, or 55 moles per liter. Therefore, pure solids and pure liquids are not incorporated. Pure solids and pure liquids this equation are not in this equation because the same thing happens with pure solid. Pure solid doesn't change. So that's why the equation looks like this. The water is pure liquid. All right, so what we do is we do this. From the table, this number is 1.8 times 10 to the minus 5 from table of K values. 1.8 times 10 to the minus 5 tells me mostly what? Reactant, product? What is it? Mostly. Or maybe closer to 50-50?
Mostly reactant.
Mostly reactant, yeah. Mostly reactant. Very little product. Well, that makes sense because there's no driving force for this. But even though there's no driving force, this tells me that a little bit of product must form. Otherwise, if no product formed, it should be 0. But it's not 0. And so, to figure out how much product forms, we do a special stoichiometry. This is an equilibrium stoichiometry calculation. With equilibrium stoichiometry, we set up something called an ice table. All right, so we're going to have to pick some concentrations here. This is what we're going to do. I'm going to pick a simple number, 0.100 molar. So we're not going to do this in moles. We're going to do this in molarity. So initially, I'm going to have 0.100 molar. This is my initial. water, remember its concentration doesn't really change. It's going to stay 55 molar all throughout, so just leave it out there. And initially, what I'm going to say is nothing has reacted yet. So we're going to just assume nothing's reacted. Of course, it's already going to have reacted because there's always collisions. You can't stop the collisions and start them. But what we're going to do is we're going to pretend we just added the ammonia to the water and no collisions have taken place yet. And so this is why we have 0 and 0, because nothing's happened yet.
Is 0.1 molar just a number that you made up?
Yeah, it's a given. Um, 0.100 molar is kind of a common number because then we can think in terms of percentages pretty easily. All right. Is there going to be complete reaction here? Do I have 100% reaction? No, in standard stoichiometry it'd be easy. In standard stoichiometry, which we did many chapters ago, all the reactions are 100%. And so if we were to calculate the theoretical yield, we automatically have to assume that the reaction is 100%. So, for example, if we're going to burn the paper, 100% of it is going to combust. And then we're going to figure out how much CO2 is produced, you know, from that 100% combustion. But in this case, look at the driving. There's no driving force. So, of course, we aren't going to get 100% reaction. If we got 100% reaction, this would be so easy. How much? Well, water is excess. This is limiting. We're going to be left with 0 molar limiting. And how much of this we're going to form? 0.100 molar, 0.100 molar. That's all the stoichiometry we've done. The next question is there 0 reaction? No reaction? No, there's a little bit of reaction here. This is what we call weak electrolyte. Weak electrolytes have a little bit of reaction. How much is that? I don't know how much that is. And so what we're going to do is, since I don't know how much is going to react, I'm going to call it X. So I'm going to have something less than 0.100 mole or moles per liter react. We'll call it X molar. This is going to be plus X molar. And this is going to be plus X molar because for every 0.100 moles per liter of this that reacts, I'm going to form 0.100 moles and 0.100 moles of that. So it's all 1 mole ratio. And so at the end of this is my change. C is change. And E is equilibrium. You know, equilibrium is we've reached a state where there's no more change. It's a dynamic equilibrium, of course, but it's pretty much the end of the reaction. And so what I'm going to end up with here is 0.100 minus X molar, then X molar, and then X molar here. And so my goal is to figure out what X is. Now, can I figure out what X is? No. I can't figure out what X is, and so what I need is a situation where I need, this is a case where we need multiple equations, at least one equation. I mean, X has got to equal something. And so what we're going to do here is this. K is not for the initial concentrations. K is the ratio at the end of the reaction. And so let me add this. The E stands for equilibrium. And so at the end, the ratio has to be this, and that's where it's going to reach its final resting place. And so what we're going to do is we're going to do a substitution. We do a substitution. K is the equilibrium concentration of ammonium. Well, the equilibrium concentration of ammonium is X, times the equilibrium concentration of hydroxide, which we call X here, divided by the equilibrium concentration of ammonia, which we call 0.100 minus X. 0.100 minus X. And then this is going to equal, well, it's got to equal 1.8 times 10 to the minus 5 because that's the equilibrium ratio that we need at the end of the reaction. And then we just solve this for x. You know, this is going to be x squared. I'm going to just do some simplification here. This is 10 to the minus 1. This is 10 to the minus 5. So 10 to the minus 1 times 10 to the minus 5 gives us 10 to the minus 6. Is that correct? And so this is going to be x squared is equal to 1.8 times 10 to the minus 6. Oh, yeah. Minus 1.8 times 10 to the minus 5x. Okay, then we're going to get this into quadratic form. X squared plus 1.8 times 10 to the minus 5x minus 1.8 times 10 to the minus 6 is equal to 0. Then I asked you to, if you could get one of these fancy calculators. The reason I asked you to buy one of these fancy calculators is because Chem 1B. If you don't have one of those fancy calculators, well, we're going to use a web-based calculator.
What would you do if the molar ratio was different? So if n is something other than 1?
Okay, if it were, for example, if this were 2, then I'd let's say plus 2x. So
And
for
then-
every x, I form 2 of these.
So then you multiply over there like 2x times x on the top?
Yeah,
Okay.
exactly. So I do that. I'm just going to keep it simple. You do that in Chem 1B for sure. And so what your calculator has, if you got one of the Casillos or if you have an equation solver, you just plug in the A, the B, and the C. And so here, what is A? 1. And then you do this in the calculator. B is 1.8 times 10 to the minus 5. C is minus 1.8 times 10 to the 6 times 10 to the minus 6. All right, then I have my x values here. Unless you could use the quadratic formula, of course, but if we can avoid using the quadratic formula, we can save a lot of time on tests. And so, well, can x be negative? Is it possible to have a negative molarity? No, so x cannot be negative, so x has got to be plus 0.00133. And so negative 0.00135 is not possible. Negative molarity is not possible. And so this is what my x is here. And so the ammonium concentration is going to be 0.00133 molar. The hydroxide concentration is 0.00133 molar. And then my ammonia concentration is going to be 0.100 minus 0.00133 molar, which is going to give me 0.09867 molar here. And so in other words, this is why I like 0.100, because if I do 0.100, then 1.3% reaction. So we had, do you see that? 1.3% reaction. And so it wasn't no reaction, we had 1.3% reaction.
Wait, how did you get the percent?
I just moved the decimal 3 over, so that's 100, out of 100, 1.3 reaction. Mentally, that's what I did. So this is how we do Chem 1B style stoichiometry. In Chem 1B, we have a lot of reactions like this where there's partial reaction, not complete reaction, and there's not zero reaction. And so Chem 1B stoichiometry is to figure out what little bit did react, or maybe it's a lot more than a little bit reacted. But in other words, we did have a little bit of reaction. So 1.3% of the molecules had enough energy, had the right, what else do we need in addition to energy in the collision for reaction to occur? Orientation. So we had the right energy, we had the right orientation for reaction to occur.
Now this is very important because this is going to lead to pH. So for example, what is the pH of this? If I asked you what the pH of 0.100 molar ammonia is, could you tell me? No, because pH is the power of the hydrogen ion concentration. So from this, though, we can figure it out. And so from this, we're going to get something called the POH, and then we can figure out the pH based on that. And so the POH is going to be the negative log of the hydroxide ion concentration, which is 0.00133. And so what does that come out to? .87. So this is 2.876. Therefore, the pH is equal to what? Well, it's going to be 14.00 minus 2.876, which is going to give us 11.123. But I want to double check my calculation, and this is something you could do as you get. If there's a way to double check this calculation, that would be wonderful. And there is a way to double check this calculation. The way I double check equilibrium calculations is I plug this in. What should this ratio equal? The ratio of products to reactants should equal 1.8 times 10 to the minus 5. Can you look at this ratio and tell me, is that the right ratio, 1.8 times 10 to the minus 5? No, and therefore our double check is just going to be to check the ratio. Check ratio. Our calculations yielded this. It gave us 0.00133 for the ammonium times the hydroxide, 0.00133. Now, K's, do they have units or no units? These are unit-less. There's reasons for that, which we aren't going to talk about, but this is why I'm ignoring the units totally. Divided by, what's the concentration of the ammonia?
0.098. Is that 6, 7, or 7?
6, 7. 9867. 0.09867. So what does that ratio come out to? And so 0.00133, square that, divided by 0.09867. 1.792 times 10 to the minus 5. Does that check out?
Yeah.
Yeah. We round it to 2 sig figs, we get 1.8 times 10 to the minus 5. And so we got the right ratio here. So this is it. We can calculate the pH. Because do bases ionize in water, or do bases hydrolyze in water, or can they do both, ionize and hydrolyze in water? In other words, bases change the pH. So how does ammonia change the pH? Ammonia changes the pH because ammonia is a base, and bases do what in water? Hydrolyze. Bases hydrolyze in water. When bases hydrolyze water, they create hydroxide. And the hydroxide changes the pH. There's a seesaw relationship between hydroxide. This is not a high concentration here of ammonium and hydroxide. But those ammonium and hydroxide we can use to do things with. One of the things we could do is, tell me some properties of hydroxide. It's a strong base. We could use that to Neutralize acids, I suspect. What else could we do? We could, are there any metathesis properties for hydroxide?
Insoluble.
Yeah, we can form insoluble hydroxide. And so an example of this would be this. So we did this. This is our understanding of ammonia and water. Ammonia and water is going to produce this. Now, once we have some hydroxide produced, we can take advantage of this reaction for metathesis. Ammonium doesn't really participate much in metathesis reactions, but hydroxide does. And so we can precipitate ions like magnesium. So let's look at an application of this. Is using aqueous ammonia to precipitate hydroxides. So what's going to happen here is this. If I have magnesium ions, do they like hydroxide? Yeah. And so if there are any magnesium ions present, the hydroxide will react to precipitate out milk of magnesium or magnesium hydroxide. So then there's something called Le Chatelet's principle. Le Chatelet's principle, you guys recall? Le Chatelet's, in your own words, can you describe what Le Chatelet's principle is? I didn't spend any time on this slide because we just went straight to the examples. So based on the examples that we did, for example, this one, in your own words, can you tell me what Le Chatelet's principle is? Remember doing this one? Where we increase the H2S. You know, this system was already balanced. It was perfectly balanced, whatever that balance is. You know, the balance depends on what the K is. So this would be reactant heavy, and the balance is going to be described by small k or a big K. This would be a small k, it's mostly reactants. Well, that's what we got here. This is small k because it's mostly reactant, very little product because the product is much higher in energy. So this is just a balance in terms of energy. Which side's more balanced, which side's more favored. So once that balance has been achieved, let's say, I don't know what the balance is here. It could be like 50-50, it could be mostly product, or it could be mostly reactant. But once that balance is achieved, what happens if I upset that balance? By adding more H2S. If I add more H2S, yeah, it's going to shift to the right or shift to the left?
if I add more H2S, it makes this end go down more. And in order to reset the balance, I need to tilt it. Remember, the balance has to be a constant ratio. And so it's going to shift to the right. And so in your own words, how would you describe that, Le Chatelet's principle? Well, if not your own words, probably the best is just to memorize what you might want to just do is just memorize this definition, and then later on, maybe try to reframe it in your own words. I just skip this one.
Can you explain it a little better? I don't really understand what it means by processes tend to partially counteract the initial change.
That's why I skipped this slide, so you could come up with your own. I mean, it's very simple. If you upset the balance, things are going to shift to try to reestablish a balance. That's all. The way I do this, so since I have more time in Chem 1B, I do it like this. This balance favors the reactant or the products here. It is the reactant. So this is the balance I have. The reactants are heavily favored. So imagine this is a U-shaped tub, and you fill it with water. If you fill it with water, then the water level on the left and the water level on the right will have the same height. That's the balance here. But in order to get the same height, we need a lot more reactant than product. And so if I added more ammonia to this side, then that's like adding more water. Let's add 5 more gallons of water to the left side. Is it happy like that? If I add 5 more gallons, then this side's going to grow higher. Say it grows up here. It's not going to stay like that, is it? What's going to happen? Water's going to shift to the right, so we get forward reaction, shift right. And so the way I envision this is something similar to this.
So if you get more reactant, you're going to make the hill tilt more to the right?
Yeah, you got it. Now the balance is all screwed up. You got too much reactant, not enough product. We need to maintain the balance. What's the balance? 1.8 times 10 minus 5. That's the ratio. Whatever it is, it's got to have that ratio. Because then everything's properly balanced. Well, the interesting thing is we aren't going to come to the exact same balance. What's going to happen is this side's going to go down, this side's going to go up, and we're going to have a new balance. But the ratio is going to be the same. This is Le Chatelet's principle. Well, speaking of that, what happens if I remove hydroxide? How can I remove hydroxide? One way I can remove hydroxide is by reacting it with magnesium 2. If I remove the hydroxide, that's like taking water out. If I start pumping water out the right side, which way is it going to shift? If I start removing water from the right side, let's say I remove half the water that was in here. Is that the stable balance? Is that the ratio? No. What's going to happen? It's going to, it's going to shift right. And so if I start removing hydroxide from here, Le Chatelet's principle says I'm going to form more hydroxide to try to reestablish the correct balance. Does that make sense? Well, this is review. I'm spending some time reviewing because I went through the chapters pretty quick. And so I just want to show you how we would actually use Le Chatelet's principle. And so if the hydroxide is being consumed, then more is going to form. So if I just keep adding more magnesium, well, that's going to consume more hydroxide, and then it's going to continue to shift the balance over. And so I need 2 hydroxides for every magnesium 2 plus. And so this is going to be the net reaction. So what I'm going to do is this. I'm going to have acid-base followed by metathesis. But I'm not going to show 2 reactions. I'm just going to show the net, the overall reaction. for this. And so this is the application. So if I take something like magnesium chloride, the chloride's not going to react. And it's just going to supply magnesium ions. This ionizes water. Plus 2 ammonias, plus 2 waters. 2 ammonias and 2 waters will give us 2 hydroxides rather than 1 hydroxide. This is going to produce magnesium hydroxide, solid, plus what? Plus ammonium plus chloride. So ammonium and chloride forms ammonium chloride. So we'll need 2 of those to balance it. And so this is our net overall reaction. And so this is metathesis reactions using aqueous ammonia and I skipped this. I skipped this at the very beginning of the semester because I was going to come back to it, and I'm coming back to it now. So let me talk about that here. Yeah, I'm sorry? Can you repeat that?
Sample exam number 4, is that just for chapter 14?
I didn't look at it. Is that what it was? And if that's the case, unfortunately, it's wrong. It should be more chapters than 1 chapter on the exam. Let me just take a look at it. Sample exam number 4. Have you looked?
No, but that was the one that we were going to go over in class because you were going to include chapter 14 on the last test, and then you didn't include chapter 14, so we didn't go over this.
Oh, yeah, okay, then it's gotta be here. It's here. Yeah, we started going over it, but it's not just chapter 14, there's also 15, 16, 17. Yeah, take a look at example. But for right now, I just wanna take a look at this. This is from the first week. All right, and so here's an example of using aqueous ammonia in metathesis reactions, except in this case it's just going to be with a magnesium nitrate rather than magnesium chloride. But can you do this one? Can you write out the equation for me and tell me the driving force? Yes. I skipped this one back when we were doing this in the first week. We just want the net overall reaction. And the reason we want the net overall reaction is like this. So let me leave this for just a moment and talk about Have you heard like the metabolic cycle? You know, like if you were to eat food, what happens to it? And so it's actually quite complicated. This is a part of it. Part of it's called the citric acid cycle. The citric acid cycle's, making energy basically. But do you want to know every little step here? When you eat food, what happens? When you eat food, you digest it and you get
energy and whatever else, right? And so when we eat like sugar, we just care, what is the overall reaction? We don't care about every little step that happens here. And there are a lot. The same thing with this. When I do metathesis using aqueous ammonia, do I care about the Bronsted acid-base reaction? Do I care about K, 1.8 times 10 to the minus 5? Am I going to do an ICE calculation? No, I just want the overall net reaction. If I eat food, I'm going to digest the food, I'm going to get energy, and I'm going to exhale CO2 and water. Right? I'm going to burn the sugar in my body. And so the same thing here. Yes, there's hydroxide. Yes, we need hydroxide to precipitate out the magnesium, but that's one of these, intermediate steps here. Am I actually putting in hydroxide in here as a reagent? It's like some people, they'll want to do this, okay, there's pyruvate here. Do you eat pyruvate, or is that coming from something else? It's coming from your food. You aren't going to a supplement store buying pyruvate. Well, maybe you are, but let's say you aren't. That pyruvate is coming from somewhere else. So one of the common mistakes that people do here is they'll write hydroxide, ammonium and hydroxide. You aren't going to the store to buy ammonium hydroxide. Ammonium hydroxide is a result of the acid-base reaction between ammonia and water. And so all we want to know is, okay, this is what we're going to eat. We're going to eat magnesium chloride, ammonium, and water. What are we going to spit out? We're going to spit out magnesium hydroxide, right? And so what I want you to do is I want you to write the overall net reaction for this. I want you to write the CE, this is a review for the final, by the way, too. I want you to write the CE, the IE, and the NIE for this and tell me what the driving force for this reaction is. Can you do that for me?